Unit tests is how we as developers keep the chaos of a changing world at bay. By programmatically documenting how our code should behave, we ensure our code continues to work even as things change. However, traditional unit tests feel limited. If we write one or even a few tests, how much of the entire space of valid inputs have we really tested? What if there is some boogeyman input lurking in the vast, untested space of valid input that would break everything? What if, instead of specifying the desired output for a small set of predetermined inputs, we could randomly sample from the entire input space and check some easy-to-verify properties of our results? If we could do that, then the more examples we try, the more confident we become that our code works. And if our function doesn't work, wouldn't we rather discover it before our users do? This technique of generating data and verifying the result satisfies invariance is called property testing. It's a powerful technique for creating robust, well-tested code. Let's look at a slightly less contrived example. Suppose we've written the first ever sorting function. Unlike our addition example, we can't just check that the output matches some other implementation of sort because it's the first one. How can we use property testing to make sure our implementation is correct? While it might be hard to take an unsorted array and arrange its elements in sorted order, it's much simpler to merely check if an array is sorted or not. We only need to check two things. First, we need to check that the elements of the output are in increasing order. Second, the output must contain the same elements as the input. We can implement these checks in only a few lines of code. In our first assertion statement, we can check that each element in our list is followed by another element that is at least as large. In our second assertion statement, we can check that the input and returned lists have the same elements, ignoring order. Combined, we can verify that our sort function works correctly on arbitrary input. We achieve this without exhaustively enumerating the correct answer or having some reference implementation that we could compare against. However, something is missing. Although we've built out the functionality to test on arbitrary input, we still initialized x to be some fixed value. How should we generate arbitrary input to feed into our property tests? Enter Hypothesis, a Python library that makes property testing easy. With an entire collection of highly customizable and composable strategies for generating data, the Hypothesis library believes that most things should be easy to generate and everything should be possible. A strategy is, at its core, a random number generator. As users, we select or construct strategies that are appropriate for generating the type of data we need, potentially modify some parameters to affect the shape or domain of the data we generate, and Hypothesis does the rest. Let's start with some simple examples. For convenience, we import the Hypothesis strategies modules as ST. We can construct an ST Boolean strategy and interactively draw examples from it using the example method. Hypothesis has strategies for other scalar types as well, including integers, floats, complex numbers, and dates, just to name a few. Strategies can be customized. Here, we set the min value to be 0 for both of these strategies and max value to 100 for the second strategy. Beyond these scalar types, Hypothesis has several strategies for constructing containers composed of other types. Let's take a look at a few. If we pass an instance of the float strategy to the list strategy, we can generate lists of floats. Similarly, if we pass two instances of the integer strategy to the tuple strategy, we can create tuples which contain two integers as their elements. We can continue to compose strategies to generate more complicated data. Here we use both the list and tuple strategy to generate lists of tuples of pairs of integers. Although we've covered a lot of ground, we're really just scratching the surface of the sort of data that Hypothesis can generate. While I could continue to illustrate each and every built-in strategy, I think it'll be better to push forward and make a real property-based unit test. But first, we need to talk about the given decorator. The given decorator accepts strategies as input and converts test functions into randomized tests. More broadly, given is the key to unlocking all the functionality the Hypothesis library has to offer. Using the given decorator has many advantages over the example method we have used so far, or other randomization libraries such as Python's built-in random module or numpy.random. With given, not only do we get an interface for generating random data, but we also get test reproducibility, caching of failing examples, and shrinking of failing examples to smaller, more interpretable cases. Now that we know the benefits of using the given decorator rather than generating random data ourselves, let's convert our sort example from earlier into a property-based unit test. we'll need to import two things from the hypothesis module. Namely, we'll need the given decorator and the strategies module. Next, we'll need to add the given decorator to our test function. We'll provide a strategy that generates lists of integers. We add an input argument x to our test and remove the hard-coded value for x. Running PyTest, we see that our test passed, not just for a single input, but for hundreds of examples generated by hypothesis. But what would happen if we weren't so lucky and there was a bug in our code? Here, we've added a new sort function, myBadSort, that will be correct as long as the input does not contain 100 and the length of the input is not divisible by 2. If we run PyTest again, you might be surprised to find that the test passes. This is because our failure case is so rare that hypothesis didn't find it given the limited number of examples it tried. Let's try increasing the number of examples and seeing if hypothesis can get it. Returning to our tests, we import the settings decorator and increase our max examples to 5,000. Running PyTest again, we see that hypothesis found a falsifying example. In particular, a list containing 3 zeros and a 100. This probably wasn't the first error hypothesis stumbled across. When hypothesis finds an error, it attempts to shrink it to make it smaller. In this case, hypothesis was able to shrink all the other integers to 0 and shrink the length of the array to 4. With a small failing input and the error message from our assertion, hypothesis helped us identify a bug in our code that might have been difficult to discover otherwise. Property testing is a powerful and, dare I say, enjoyable way of testing your software. As you go forth and apply it to your own code, I have a few parting thoughts. Property testing benefits from creativity and practice. The more tricks you learn, the more widely you'll be able to apply them. To get your creativity flowing, take a look at the Hypothesis Ghostwriter documentation. There, they describe some of my favorite styles of property tests. And finally, a word of caution. Property testing won't always be the right tool for the job. A function's output might not have any nice properties to verify, or a function might be too slow to run for hundreds or thousands of examples every time you run your test suite. But that's okay. Property and example-based tests work together to help you and your users sleep soundly, knowing there aren't any boogeyman bugs about.